Okay, let's do it. I'm going to go ahead and tell you this problem is not hard, but bulky. It's like a bulky problem. There's a lot there, and it's very easy to make a mistake at some point, but let's just do it. I have it written up there, so you have to do it. It's the two-body problem. The two-body problem. Yes, the three-body problem was a book and a movie. It was pretty good. It was okay. Show. And the two-body problem is something that we can solve. The three-body problem is not analytically solvable. That's what makes it so awesome. The two-body problem is the following. I have two objects that are gravitationally interacting with each other, and I want to take that system and make it an equivalent one-dimensional problem. It's kind of a magic that we can do all that thing. So we have to go from 6 degrees of freedom to 1. That's pretty tough. So let's talk about this and let's model this in Python first. And I already have the program. I'm not going to build the program for you. I'm going to show you my Python program, give you an overview, because then we can use that to test different things. Okay. So suppose I have these two masses, m1 and m2. They're at a position r1, r2, and the distance between the vector separating them is the vector r, such that r is r2 minus r1, just normal things. And then I have the gravitational force on, this is actually on mass 1, negative g, m1, m2, over the magnitude of r times r hat. And this has the gravitational potential, which is going to be important later, that only depends on the scalar value of r. Okay, negative g, m1, m2 over r. If I define force as the change momentum, over some short time interval, short is relative, the short time interval, P12 is the momentum at the end of the time interval for object 1. P11 is momentum at the beginning of the time interval. And then I can divide it by delta t, solve for P12. This is my momentum update formula. I do the same thing for object 2. It's going to have an opposite force, right? I only have to calculate that force once. And then I can say that the momentum is the change in position. Oh, that's wrong. Divided by, this is, the momentum is, there's a mass. I put it down there. All right, see, yeah, okay. And then so I can update the position for both of them. Let's run this thing and just look at it. Okay, so here is the code for my double star binary star system. So I have the gravitational field G, I have M1, M2, I just pick star-like masses. That's the total mass. We're going to use that later. I have my little notes there. I don't want to lose my notes. Because you know I'm going to make a mistake. I told you I'm going to make a mistake. We're going to power through. I've already tried this once before, and I did make this video before, but it was a presentation. I like this better. My stars are objects. There's my initial momentums. Don't worry about that stuff. We can look at that later. And then here I am, right? There's calculate R, calculate F, update the momentum, update the position. Let's just run it. Not in real time, because that'd be weird. So there's my two masses gravitationally interacting with each other, and that's where we want to kind of take this system and move it into a one-dimensional problem. Okay, great. So let's go back to the board. And let's just think about how we would represent this as a system using Lagrange equation, right? So Euler Lagrange said the Lagrangian is T minus U. And so we want to think about the kinetic energy. So, I have object R, position R1, I have position R2. Imagine that I say R1 is the vector X1, Y1, Z1 in Cartesian coordinates, okay? So if that's the case, I can find the velocity, which I'm going to write as R1 dot. It's just going to be the derivative of this respect of time, x1 dot, y1 dot, z1 dot. Okay, that's cool. Now, this light's kind of bothering me. Let's adjust that a little bit. Maybe that's better. It's kind of early, so my lights are a little messed up. So this is a weird notation, r1 vector dot. It's the velocity for object 1, but it's kind of useful. Now, in the kinetic energy, we're going to have to square that velocity, the magnitude of that velocity squared. So I'm going to write this, r1 dot squared, which you can't do. What that really means is the square of the magnitude. So that's just, it's in Cartesian coordinates, that's easy. x1 dot squared plus y1 dot squared plus z1 dot squared. So we can do that, and that's the point I'm trying to make. Okay. So with that, I can write the kinetic energy fairly easily. T is 1/2 m1 r1 dot squared. There's that r1 dot squared I just told you about. It's kind of weird. Plus 1/2 m2 r2 dot squared. Now, if you think about, and we have the potential energy too, but I don't really care about that. If you think about this in terms of degrees of freedom, that's a three-dimensional vector, that's a three-dimensional vector, and that's where you get the 6 degrees of freedom. Okay, so that's not cool. We don't want to deal with 6 degrees of freedom. Now, I want to switch this over to 2 different variables. I want to describe this by the vector r, and remember r is r2 minus r1. That's the relative position from one object to the other. And then I want to use the vector capital R, which is the center of mass. So I'm going to assume that you've seen center of mass before, but I can write this. R is going to be equal to m1, that's the lowercase r1, plus m2 r2, all of that over m1 plus m2. Now that plus m1 plus m2 comes up all the time, so we're just going to call that m. And it's technically capital M, but I'm very kind of sloppy. But see, these are our 2 variables, and they both have 3 degrees of freedom. And so you think, well, that's not really going to help. It's going to help, trust me. You know it is. Okay. So I want to get R1 in terms of, I want to get this, which what I want to do. See, I've already made a mistake. I want to get, so up here I can solve for R1. This is important. R1 up here is going to be equal to R2 minus R, right? That's from that. And then R2 is R1 plus R. So let's rewrite the vector R. Yep. I want to get, let's solve this. I'm going to rewrite this, and I'm going to get it in terms of, I want to get R1 in terms of capital R and lowercase r. So I'm going to take this, and I'm going to substitute in R2. So this is tedious, and a lot of the books just kind of like gloss over this. So I'm trying not to gloss over it. So R is equal to m1 r1 plus, and I'm going to write this over m. I'm going to break it up so it's easy. Plus, now I'm going to say m2 times r2, but I'm going to use that for r2. So plus m2 r1 over m plus m2 r over m. So all I did was to take this and plug it in there. And so this says that r is equal to, I have r1 and r1, I can factor that out. I get m1 plus m2 over m r1 plus m2 r over m. And this m1 plus m2 is m, so that cancels. So this is really important. I'm going to put it over here. If I solve this for r1, I get r1 is going to be r minus m2r over m. Can't see that. Camera adjustment time. I think I kicked my camera. Okay. Now we're going to do the same thing, but get r in terms of r2. So r, up here I'm going to substitute in r1, I'm going to put that in. So I have m1 r2 over m minus m1 r over m. And then I have that last term, this one, plus m2, I'm putting it up here, m2 r2 over m. And again, I can combine these two, and I get m1 plus m2 over m r2. And then I have minus m1r over m. Cancel, cancel. So if I solve that for r2, I get r2 equals, where am I at? Right here. R2 is going to be equal to r plus m1 r over m. Very important expressions, very important. Okay. So now I have r1 and r2 in terms of capital R and lowercase r. And I can put that in my kinetic energy. Now, we should say something here, right? We should, and I'm gonna. So if I take the derivative of this, I get the derivative of r plus minus m2 over m derivative of this r. So the derivatives still work. Everything's in Cartesian coordinates. Okay, so I can still do that. Let me just write that out here. I'll erase this later. r1 dot is equal to r dot minus m2 r dot over m. That does work. And the same thing over here. r2 dot equals r, that's a dot, dot plus m1 r dot over m. Now I can plug those in up here, right? So I have the derivative r1 dot and the derivative r2 dot. I can plug that into my kinetic energy term. So T is 1/2 m1. Now r1 dot squared is going to be this squared. So I'm going to write that as r dot minus m2 r dot over m squared plus 1/2 m2, and then I have r dot plus m1r over m squared. So I wrote the kinetic energy in terms of, instead of r1 and r2, I have capital R, the location of the center mass, and r, the relative center mass. Now we have to square these, and maybe this is something I'm going to skip, but you might want to take time to yourself and say, okay, if I wrote this as a Cartesian and that as a Cartesian, and then I found the magnitude and squared it, it's the same as like foiling out this whole thing. So let's do that. T is 1/2 m1. So I'm just going to do the whole thing, right? Let's just put this right here. So I have r dot squared, which is again the magnitude of r quantity squared, and then I'm going to get two of these terms, minus 2 m2 over m r dot, and then I get that squared, plus m2 squared over m r dot squared. Now I'm going to put the second term down here, plus 1/2 m2, and I get r dot squared, plus 2 m1 r dot. you know, okay. R dot, r over m plus m1 squared over m squared r dot squared. Okay, so now when I multiply this out, let's just do that with the magic of math, of erasers. So I'm going to have m1, 1/2 m1, 1/2, that's going to cancel with that, m1, and then I have plus 1/2 m1. And then down here I get this. And then that goes away. I have m2. And then I have 1/2 m2. Okay, right away, boom, boom. That cancels. And let's get the r terms together. So I have T is 1/2 m1 plus m2 r dot squared. And then the other term I have is plus 1/2. Okay, so here I have these two terms. I have 1/2 m1 m2 over m squared, and then 1/2 m2 m1 squared over m. So I can factor out an m1 plus m2 times m1 m2 over m squared r dot squared. That's a tough one. Okay, but you can see that. And then so that cancels that, and I get m1, m2 over r, and I did it. Okay, so now we have our kinetic energy just looks like this. That was probably the hardest part, just so you know. T is 1/2, that's capital M r dot squared plus 1/2 mu r dot squared. And so here mu we call the reduced mass, where mu is m1, m2 over the total mass m. I mean, it looks like we really didn't do anything because we went from 6 degrees of freedom to 6 degrees of freedom, but we did something really great, okay? Because now let's just apply the Euler-Lagrange equation. Let's just do that, and let's do it in a very generic way, okay? So I can say L is 1/2 m r dot squared plus 1/2 mu r dot squared minus u of r, right? And notice that u of r depends on the little vector r. It does not depend on the center of mass, and that's important in this two-body problem. Now, when I apply the Euler-Lagrange equation, it says the partial of L, and I'm going to write this as a vector, even though, you know, let's just do one of them. Let's just do one of them. The partial of L with respect to Rx minus the derivative with respect to time, partial of L with respect to Rx dot is equal to 0. Well, if I go through and I take the partial of L with respect to Rx, there's no Rx, so that's 0. And that means if I take the partial of L with respect to Rx, I'm going to get this. The derivative with respect to time of, if there's an Rx in there, I get m Rx dot equals 0. Okay. So that means that mRx is equal to a constant. And I could do the same thing for the y and the z directions. So what I get is, I'll put it over here. I told you I was going to erase some stuff. I get this very important thing. R dot equals a constant vector, right? The motion of the center mass has to move at a constant velocity. And that's because there's no potentials that would change that. The potential has no dependence on the center mass, so that has to be true. Okay, now with that, we're going to make a simplifying assumption just so we can proceed. I'm actually going to assume the velocity is 0, right? If it's not 0, I can solve the problem and then I can give it the center mass velocity later. That's fine. And even more, if the velocity is constant, I can I can pick. If the velocity is 0, I can pick the location. Let's make it easier on ourselves. Let's say the position of the center mass is 0, too. Again, you don't have to do that. We can fix that later once we solve the whole problem. Okay. So, but now we've gone to a situation where this doesn't even matter. I only have this term. So I actually did do something very important, right? We went from 6 degrees freedom, 3 and 3, to just looking at the motion of this relative motion of the reduced mass, which is just 3 degrees of freedom. Kind of a big deal. Okay. We're making progress here. So now let's just go back to our system of R1 and R2 just for a moment. And if R is 0 and R is 0, then this is pretty easy. R1 is negative M2R over M. R2 is negative it's plus M1R over M. Now the next thing I want to look at is the angular momentum of the system. And so here we define the angular momentum of a point as L with the vector, so it's not the Lagrangian, it's got a vector right, so you know it's not that, is equal to R cross P. So for my two mass system, this is going to be R1 P1, where that's momentum, plus R2 cross P2. Okay, so now I do have a little thing here. We have the cross product. If I take the dot products of these, this should be okay, right? So I'm going to say L, the total, is equal to R1, and I'm going to switch everything over to R. right? Because I have two variables, but I don't really need r. So r1 is that. I'm going to write it as negative m2 over m. And now I'm going to have the momentum is mass times velocity, and I switch this to when I take the derivative, that's my velocity. So I'm going to get another one of these terms squared, and then I get r cross r dot, right? Because there's a wait, and then I have an m2. No, then I have an m1. So there's going to be an m1 in here too, because that comes with that one. Yeah. So I get twice of these because I'm switching from r to r, and then r1 to r1 and r1 dot to r1. Now the other term, I get two of those, m1 over m quantity squared, and then I have an m2, and then I have r cross r dot. So I can factor out the r cross r dot, and I get L is going to be r cross r dot. And then I have over here, I get m1 plus m2. Oh, this is really complicated. So I have, I'm going to cheat. Let's see, what was it? Cheating. I got that part. Okay, here it is. I get m1 r dot m1 m2 over m squared times m1 plus m2. That's right. And then that cancels one of those. So I get the angular momentum is actually really nice. It looks like this. Mu, remember that's my mu, my reduced mass, r cross r dot. Cool, right? Okay, now when we talk about angular momentum, we use the angular momentum principle. It says that the net torque about some point is the derivative of the angular momentum with respect to time. But if we have no net torque on the system, we only have that central force, then the net torque would be 0. So that means that the angular momentum is constant. Constant angular momentum. You know, I'm going to take a moment here because I just realized I forgot to do this. I did want to show you the motion of the center of mass back in the Python program. So I showed you that we can reduce the problem and set the center mass equal to 0. And I'm going to do that. So let's switch over here, and then we'll come back over here and do something else because I do want to show you something. So here's my program. Notice that my center of mass is not stationary. And in fact, these things are moving up. Okay, we can plot that if you want to. I'm not going to plot that. But what I want to do instead is to set, I can set the momentum to 0, the net momentum to 0, if the two objects' initial momentums are equal and opposite. So here I have the momentum of star 1. I'm just going to change this momentum of star 2 to the opposite of that, and let's see what happens. You'll notice that the motion looks the same, right? Except that the objects come back to where they started from. They don't actually drift off into space. So that drifting off into space is at a constant momentum. We could actually plot the center of mass of the system, and you'd see it's just moving at a constant line. So we'll just put that center of mass at the origin, and that's what we did here. And it's a much simpler problem. Okay. I'm not sure how much I'll mess with the code to show you. I'll probably do it in another video. I won't do the derivation. I'll just do the coding for the whole thing. Okay. Oops, my camera. Okay. So if the angular momentum is constant, let's just pick a value for the angular momentum. And we're talking about just the vector r. Okay. So I'm going to say that what if I say r is equal to x, y, 0, and then r dot would be x dot, y dot, 0 dot, which is 0. Let's just go ahead and find the angular momentum and take the cross product. L equals mu r cross r dot. Now, how do you do the cross product? Well, in Cartesian coordinates, we can use the determinant. So it's going to be mu times the determinant of x hat, y hat, z hat, x, y, 0, x dot, y dot, 0. So if I take that determinant, I say L is equal to mu times, and let's just write this as a 3D vector. So I'm going to expand about this x, and I get y times 0 minus 0 times y dot 0. Then I'm going to expand about this. I have a negative sign, so I have 0 times x is 0 minus, or x dot x times 0, which is 0. And then I have the z component. I have x times y dot, x, y dot, minus y, x dot. And you'll notice that this only has a z component, and that's important. So Lz is equal to this thing, and we said the angular momentum has to be constant, okay? So this is a constant number. And we'll come back to this later. But the important thing is if the angular momentum is constant, then I could pick that the motion occurs in the xy plane. And that's what I'm going to do. Okay, so let me show you. You can't not have a two-dimensional motion. You may have it not in the xy plane, but it's going to be a two-dimensional motion. So if you go back over here to the computer, let's run this. And remember, Web v Python is 3D. I'm going to let it orbit a little bit, just so you can see. And then this is flat, right? It has to be flat. So no matter what you do, and you can try that out, it's going to be a flat system. And again, I'll make another video where I animate these things just for fun, because I think it'll be awesome. So if that's true, then I don't need a z component. So I didn't switch to my camera. I don't need a z component. So now I've gone from 3 degrees of freedom to 2 degrees of freedom, right? I only need x and y. Because angular momentum should be conserved. So now I have this. Here's my reduced mass. It has an x and y value, right? That's what we've been dealing with. And I can represent that with a vector, with polar coordinates, r and theta. Okay. So in polar coordinates, and I'm not going to do this fully, but I can write the Lagrangian in polar coordinates, and that's what I'm going to do. Okay. And that's the scalar value r, right? That's the r in polar coordinates. So what we do is say x is r cosine theta, y is r sine theta. And because how do I write the kinetic energy in polar coordinates? Well, I don't really know, but I know how to write it in Cartesian coordinates. So t is going to be mu x, 1/2 mu x dot squared plus y dot squared. So let's take the derivatives over here. X dot is going to be equal to, if I take the derivative of x dot with respect to time, I get r dot cosine theta plus r minus r theta dot sine theta. Now that's that mistake. I've made that mistake so many times in my life as a student. I remember this mistake. Some of those things just stick with you. I always forget to take the derivative. So you take the derivative of cosine, right? It's a product rule. And you get negative sine theta. But then you got to take the derivative of theta, and you get theta dot. Okay. And then I get y dot is going to be equal to r dot sine theta plus r theta dot cosine theta. Now when I square those two terms, let's just square them. So x dot squared is r dot squared cosine squared theta minus 2r theta dot r dot cosine theta sine theta plus r squared theta dot squared sine squared theta. I did that one fast because I've done it a billion times. Okay. Y dot squared is equal to r dot squared sine squared theta plus r squared, no, let's put this other one, plus 2 r theta dot r dot cosine theta sine theta plus r squared theta dot squared cosine squared theta. Okay, so when I add these two terms together, these things cancel. These two terms add together, I can factor out the r dot squared and sine squared plus cosine squared is 1. Over here I can factor out r squared theta dot squared, and so I get t equals 1/2 mu r dot squared plus r squared theta dot squared. Now you may say, oh, I already knew that because it's polar coordinates and just duh, right? If you already knew that, that's fine, but I think it's always important to see where that comes from. It doesn't really come from magic. It comes from I guess, derivatives and stuff. Okay, how are we doing on time? Wow. Okay, we're almost there. We've got a lot of stuff to do, though, but we're almost there. Okay, so now let's write the Lagrangian. I'm going to write the Lagrangian right here. L is 1/2 mu r dot squared plus r squared theta dot squared minus u of r, right? I don't know what that u of r term is, but I know that we have to subtract that. So I have 2 degrees of freedom, so I need to have 2 Euler-Lagrange equations. So let's start with the theta equation. So that says the partial of L with respect to theta minus the time derivative of the partial of L with respect to theta dot is equal to 0. So let's just do this in pieces. The partial of L with respect to theta, and remember, that's the Lagrangian, that's not an angular momentum because it doesn't have a vector of it, is equal to 0, right? If I go through here, there's no theta terms. So now I get the partial of L, let's put over here the partial of L with respect to theta dot is going to be equal to 1/2 mu r squared theta dot squared. So I get mu r squared theta dot. Mu r squared theta dot. Now, since the derivative of that, the time derivative of that has to be 0, that means that this has to be a constant. So let's set that constant equal to L. And that's pretty important. I'm going to put it over here. I don't think I need those r vectors right here. So let's put this right here. L equals mu r squared theta dot. Okay, so that comes from this non-theta value in my potential. Now let's do the r. The partial of L with respect to r minus the time derivative of the partial of L with respect to r dot is equal to 0. So the partial of L with respect to r is just negative the partial of u with respect to r, right? That's the only oh, no, that's not true. Okay, I do have that, but I also have that term right there. So I get plus mu r theta dot squared. Whew, almost made a big mistake there. Let's just double check I'm not way off track here. Okay, let's see. Did I get that right? Mu. Yep, mu r squared. Okay, theta dot squared. Okay, now let's take the partial of L with respect to r dot. That one's pretty easy. There's only one r dot, it's right there. So I get mu r dot, and then I take the derivative of that with respect to time, and I get r double dot. So if I put that together, I have negative partial of u with respect to r plus mu, that's a mu, that's a u, r theta dot squared equals, I can move that to the other side, mu r double dot. Now, it may look like we have 2 degrees of freedom, theta and r, but we don't because I already know something about theta. So over here, I can say theta dot is equal to L over mu r squared. So if I put in for theta dot squared, right here, I get negative the partial of u with respect to r plus mu r, and then I'm going to square that. So I get L squared over mu squared r to the 4th equals mu r double dot. Now I have an equation that only depends on r. That's kind of cool. We kind of won. We just won. Okay, but we're going to go a little bit more. So here, that cancels with one of those. That cancels with that. So I get the following one-dimensional equation of motion. So I get mu r double dot equals this stuff, which is going to be equal to, did I get that right? That's right, L squared over mu, there's one right there, and then r cubed. Yep. Minus the partial of u, that's my potential with respect to r. That's kind of a big deal. 1 degree of freedom. 1. Okay. So now what do we do? Well, if we want to think of this, we can kind of say, what if I had just one potential, right? If I have one potential, then I could turn this into a potential. So I could integrate this and make it like a centrifugal potential. That's what technically it is. So if I do that, I can say, let's just check. Let's say U effective is going to be the actual potential, and then I have to take the derivative of this, the negative of it, and I get, this is r to the negative 3. I'm going to raise that by 1 power to negative 2. I'm going to divide that, so I get plus 1/2 L squared over mu r squared. And that's my effective potential. Did I give him a negative sign wrong there? No, that's right. Okay, so this is my, it's as though I have a one-dimensional particle and this is my potential. Whatever that real potential is, notice that it doesn't have to be gravity. Notice that the only important thing about that potential is that it only depends on r. That's kind of a big deal, okay? So if I do that, I can write that as my effective potential, and I can model the motion of this system. And that's modeling the motion, assuming the center mass doesn't move, which it does, okay? So we can do that. And I'm going to make another video where I actually go through not deriving all these things, but showing all these things in WebVPython, showing the angular momentums in the constant z direction, converting this to a one-dimensional problem, and showing it's the same as my numerical model. But I think a 36-minute video, which is what I have right now, is quite long enough if you must know. Okay, so there you go. There's your full derivation of that problem. And I look at the textbooks and they always skip some steps. I technically did skip a couple steps, but that was for you. So it was really for me because I'm doing it in class. I'm going to forget. So I hope you enjoyed that. Again, wait for that next video. I'll talk to you guys later.